Hello, everyone. Welcome to this session. My name is Wycliffe Fagumba, and I want to share with you how you can obtain long-term temperature data, minimum temperature or maximum temperature for your region of interest. So let me visualize set options. Let me visualize where we want to obtain our region of interest, for example. I'm interested so much in tea, so maybe you want to set up an experiment in this tea growing region, another experiment in this other tea growing places, or um, another one up here in a region called Nandi, a tea growing region, or you want to set up an experiment in the east of Rift Valley at such a place near Mount Kenya. So it is important that you report whether temperature is one of the important, of course, temperature is one of the important factors affecting performance of tea crop. So you might be interested in showing how temperature compares among your sites. So you might be wondering whether you need to install weather measuring instruments at each of those locations and monitor. But then we have some very, very good data that span long period of time. If you search for Terra Climate in that search bar, you get a monthly uh, climate variable data from 1958. And if you click on these bands, you can see which variables you can actually extract. So for today, we are going to check Tmin and Tmax. Okay, so let's get to Colab. First of all, we will name our notebook as, say, long-term temperature, like that, so that it's not untitled. And then we start by importing a couple of packages. Basically, the two will be NAF, Earth Engine and GMAP, or EE and GMAP. Once that is done, we will authenticate our Google Earth Engine credentials, and then we initialize our project. And then we need to provide the project name, and project name we can get from your name here in Google Earth Engine coding environment. You go to project info and then you obtain the cloud project ID. That is what you provide as a parameter to the argument project. Okay. When you do that, this will you will have to allow Notebook to obtain your Google credentials. Okay, continue, and then continue, and then that should be it. So we can create map on which we will select our, or first of all, we can start with by listing our regions of interest. So let's say you want to set an experiment in a region called Kericho, you want another experiment in Nandi, or you want another place in Kisii, and then maybe Kirinyaga, and is it Embu or Meru? Let's say Meru. Those are the points you are interested in. It's just a list of points or names of those places. Then you can generate a map using GMap on which you can demarcate your points. But if already you have points or coordinates of the points where you want to set up your experiment, then you don't need to generate them manually here, the way we are going to do. So we are going to start with Kericho. So I have basic understanding of where Kericho is. So I can decide to pick a location here. Maybe somewhere inside a bit. Okay, maybe location here. So I pick this point and mark my Kericho point. Then I move north to a region called Nandi. And then let's say you've talked to these people and they've allowed you to set up your experiment in this field. So you pick a point there. Then you need another point, maybe in Kisii. I know this is Kisii region. And then you have visited this area and talked to these people about your experiment, what you want to do in their farm. And then one of them say, okay, you can establish your farm or your experiment here. And then you pick the coordinates as you leave so that next time you want to go back to your farm, you know where to go. And then you have also traveled to the east of Rift Valley and begged these people to allow you run your experiment here, telling them that you already have other experiment at other places and it will be interesting to compare your findings across locations. And finally, you have your experimental plot to be established in Meru. So we have 1, 2, 3, 4, 5 points. Okay. So once we have these are our points, we can make them a feature collection or something which we can use to extract temperature data. So let's say we want to call them our locations. Let me say sites. Let me call them sites. Maybe that's a better name. So from the map, we draw features. Then we can print our sites. There will be a list of 5 points, features. So these features represent the 5 points that we demarcated, and we can name them. So again, I can just call them as sites. And then for each, we can like loop a function. We want to set, because each of them currently has no name. They are just points demarcated here, but we have a list of names in the points here. So we can use that list to populate a column called name, which we set name as name. And then from where are we getting this? For name or for the feature itself, and the name coming from a zip of sites and points. Yeah. So now if we look at our sites, of course, there are still the 5 sites. What this does is that it sets for each feature in this list, this one is also a list, we set a name to a column name, and then that name and the feature is the combination of these sites and their names zipped together. Okay. So with that, we can now create a feature collection because we have, or we can just call it FC for now to make it simpler, which is a feature collection as a function, and then we supply the sites. So our feature collection will be 5 elements, and the first element you can see is named Kericho. The other one is named Nandi. The other one is named Kisii. Another one is named Kirinyaga. Another one is named Meru. So those are the 5 points we want to extract long-term, say, temperature values for. Okay. To confirm that they have been named accordingly, because anything can happen, we can create another map and add them on top. So we can say map1, gmap, and we provide a map function. Then we provide a base map, which is satellite. And then on that map, we can add layer, um, add layer, and the layer we are adding is the feature collection. We don't have time to do the coloring much, but we can call them sites. And then to add legend or to add labels like names on top of each point, we can use add labels. And the feature collection we are adding labels on is FC, and the column from which the labels are coming is called name. Font size, just for visualization, so that we see, it should be lowercase s. We see them clearly. We can say something like maybe 14 points. And then we can make them look white to contrast with the green color of the satellite background, for example. And that should be it. Maybe we center our map. Sorry, it's map1.center object. We center our object on FC at maybe zoom level of 9, and then we can visualize our map 1. There is an error. 2 are given where 1 is expected. So that is on Gmap map 1, and then on map 1 we add layer feature collection, and then to map 1 we add labels. Okay. That add labels was wrongly. Okay. Add labels is now correct, but then we add feature collection. The column is called name. Font size is this. Font color is white. Map init takes one positional argument, but 2 are given. Where is the problem? Okay, maybe here. We need to say base map. Okay, yeah, it's fixed it. Anyway, now we can see our 5 points named accordingly. That's a bad one. Why did I move it? Okay, I will have to find out where Kerichap is. Okay, so we stick the name. Anyway, the point did not move. It's just the label which shifted when I dragged it a bit. So it's still in that location. Good one to note. But importantly is that our points are labeled accordingly. That's where Meru is, and then the rest are also in their rightful places. Okay. So then after we have obtained our points as a feature collection, we can obtain therefore the CHAPS dataset. This Idaho TerraClimate, actually we can just call it temperature or something like that. Temperature data, and we provide a tuple. We obtain the snippet of the data set itself from this, which is the collection snippet. It's a unique ID for this data among so many data sets that are available in Google Earth Engine. And we want it all the way from the year 1958, super long time. From the first day to, let's say, 2024, December 31st. Okay, then we can print the temp, and we see that temperature here. Actually, we should have even selected the temperature, because currently it has got so many variables. So we can say select And to select temperature among the variables that we have there, you go to bands and you check which one is for temperature. And let's start with maximum temperature, TMMX. So TMMX, and then still we will have 804, I think, elements. 804 because this is 67 years and each has 12 months. So 67 times 12 gives us 804. Okay, so we want to run this along a list of years. So we will create an Earth engine list, which is a sequence from 1958 to 2024. So this is just a list containing the years, 67, 1958, all the way to 2024. Okay. The next thing is then to convert this, to create a function which will bring these several months and years to just annual data. So we can define annual temperature function, which takes a year because we are mapping it along the years. So our start year will be EE date from year, month, day, because that's the kind of structure we want to provide here, which takes the year we provide, and then one is the month and one is the day, so YMD. And then the last day, uh, the last date is the start, but we advance, like we increase that start by 1 year. So meaning from January to December. So we've jumped a whole year. And for each image, we will take the data we had, which is called temp from the collection, and then we filter it for the period we want to run our analysis on. And then after getting for 1 year, we get the mean. Here we don't get the sum like we were getting for rainfall. For rainfall, we get the sum because of total rainfall for the year, but for temperature, we get the mean. There is one variable here called scale, and it is indicated as 0.1, meaning we need to scale down our data by multiplying it by 0.1. If you watched my previous video, there is no scaling like 0 for precipitation, but for temperature, there is a 0.1. Like the numbers are multiplied by 10 for memory reasons. But now if we want to bring them down to degrees Celsius, which is the unit provided here, degrees Celsius, then we need to divide it by 10 or multiply by 0.1. Okay, so from there, what do we bring back? We bring back an image, and then we could use system start date, but I prefer just to pick the year from the year we supply for this case. Okay, so we have a function which can run through our images and then pick a mean for 1 year and reduce it to the actual degree Celsius values. So our annual temperature will be mapping on years. We map a function which we have created, which is called annual temperature. And then we wrap everything to image collection. So to wrap it, we just use EE image collection. Okay, then to the end, we can check now our annual temperature data, which is now 67 elements, and each image is annual mean for 1 year. And then after that, the probably a bit complicated function, therefore, is to reduce these images for our region of interest for each point. So we can import, actually we can import a function, a package called functools, and then we import what we call reduce to help us in the reduction. Then we define a function because we want to do this for each feature, like for Kericho, different for another location, Kisii, different for each of these. But again, we want also to run it for each image. So for each feature and for each image, get mean temperature. And the mean temperature is given by image, and then you reduce region. We used this yesterday or in our previous video. So our reducer here, what we want to use to summarize the values in the region is mean, right? That is, we want to get the mean over our region of interest. And the geometry is called, from each feature, get the geometry. After getting the geometry, we lastly provide the scale, which of course you can get from the bands here, 4638.3, which is the native scale, and we are using points, so that's fine. Sometimes you can change that scale to help you run your data faster, but for this case, because we are just working with points, it's fine. And what are we returning from this? We are returning a feature without geometry. We are not interested in the geometry of the feature, so we set geometry to none, and then we provide a dictionary of what we want. What we want, first of all, is the name. So if it is Kisii, we want to know that this is for Kisii. If it is Kericho, we want to know that this is for Kericho. And then we also need a year. And for the year, we get it from image because we assigned this as a property to each image when we were creating the annual summaries. And we also need the TMMX, which is the mean, what we calculated here, which is the mean temperature. Okay. Then finally, we return the annual. Yeah, we return the annual, which is the annual image collection we obtained here after mapping the function, after mapping the per image function on it. Okay, so that is our function. Now, what we need to do with this function, what the function does is that it reduces, it gets the mean temperature for each region, for each point, and then sets the attributes to bring back, and then we apply that to the image, to each image. Then what we return, once we have returned the annual and we have mapped the function on it, what we can now do is to get the actual values that we want. So for our feature collection, which is the 5 locations, we can map per feature, which is now the second function. And then we can see what the temperature is all about. Okay. Must return a value. There is something we are missing here. We returned this, and then after this, okay, this one should be the indentation. We were missing the indentation. So we have each of these 5 features having zero properties. Okay. We need to flatten it. I think so. Flatten this so that we can see the properties. Yeah. Yeah. So now we have 335 elements, and that is just 5 locations times 67 years. So we have 5 locations, and each of them has data for 67 years. So that's 335. Okay. Almost finally, we can get it to the best thing we want for ourselves, or the most common format we are used to, which is a data frame or a CSV or something of that kind, or an Excel. Uh, so for each of the returned temperature data, this one here, we um, we convert our feature collection, which we flattened, to a data frame. So that is feature collection of the temperature. You remember we had to wrap it into a feature collection. And then temperature DF, we can check maybe the head of it. Okay, so we have name Kericho, we have its maximum temperature, annual maximum temperature, and we have each year. If we check the tail, that is the last few, we are in Meru now, and we can see the temperatures for Meru all the way from 1958 to 2024. Finally, let us visualize this. Maybe seeing is believing, and that will import another uh, library, which is matplotlib.pyplot as PLT. Okay, after importing that, we add another cell and then we plot the figure. So PLT dot figure, and we provide a fig size as a tuple of 10 by 5. Sorry. After providing the tuple, then we say we want to group our data frame by the name and group. We create a group. So for that, in temperature DF, we group by name. Just the same way we do this in other packages like R or so. If you are used to group by in R and you want to plot several functions, you want to apply a function and group by some categorical variable. So plt.plot will plot each of them, which is for each group we pick the year on the y-axis, and we also go to each group and we pick TMMX, which is the maximum temperature. We can have some joints or points as O's, not 0, but O. And then we can call a line style, which is dash. And finally, we label each by the name. Okay. After that, we can now then add other things like plt.title to our plot, mean annual temperature. And then we can also add, anyway, we can visualize it. Okay, something is wrong. Data frame object has no attribute group by, has no data frame, has no group. It's a group by without a dash. Yeah, we have dash in R. Another error, keyboard markers. What? No, it's supposed to be marker. Okay. Interesting. So already we can see how temperature values have been changing among our sites, but we don't have legend. So we don't know which one is this cool region and which are these hot, not really hot, but warmer areas. Okay, so we can add the labels. My X and Y axis are still empty. So we can add plt.x label for that. Of course, those are years. And then plt.y label is, we can call it mean temperature. Mean temperature in degrees Celsius. Ooh, where will I get degrees? For now, let's go with just this. But we can get degree symbol and insert it there. Then we can have some lines, maybe not necessary, or can help us interpret. Okay, we can add some grid lines. So we set it to true. And then we say what style do we want for the lines. We want dash dash. And then alpha we set to maybe 0.6 so that they're a bit transparent. And then plt.legend so that we can interpret which line is which what. So we can just give them sites. And then plt dot layout, tight layout, sorry. And then lastly, we show it. Anyway, in Colab, it's shown by default. Okay, so who is the warmest? Lower temperatures in Kirinyaga, quite cold at the foot of Mount Kenya. Over the years, of course, the temperature has been increasing, you can see, but yeah, it's let me reset this so that we can fully see it. It's been warming, but generally the coldest. And then the red one is Meru in between. And then the green and blue are a bit quite close together. That is Kisii and Kericho in terms of temperature over time. And Nandi is appearing to be the warmest. Okay, depending on the location that I picked for Nandi, the exact point where we picked for Nandi, that location appears to be the warmest over the years. So this can justify why somebody is picking locations. You have their annual temperature from 1958 all the way to 2024. So you have very, very long-term data. You can talk of the mean temperature ranges from this to this, minimum, maximum, something like that. Okay, so what else do we want to do? If we want to get the minimum temperature, this is the only location we change. We just change that to Tmin. Years remain the same, the function the same, annual the same, everything the same. That's the beauty of all this. Like you struggle to create them. Something is not right. TMMN from this to this. And then we get the years and then we run this and then we get this and then, okay, here we need to change TMMX to N and then TMM. Okay, here we don't have to, but yeah, we can just change it to N also. And then now we will have the correct data also here. And now we have these lower values, 10, whatever, which are the minimum temperature values we are expecting. Again, we have to change this to N, and then actually this was the min maximum. So here we have the minimum. What about the minimum? Again, we see Kirinyaga having low minimum temperatures, 8 degrees, 9, 10, barely 10. So it's below 10 most of the years. Again, this is the mean for the year. So sometimes some months can be higher than that. Okay, but in the green one, Kisii, the minimum temperature in Kisii is quite warm. I think this is now contrasting with what we were seeing for Nandi. Where is Nandi now? for the minimum temperature, it is quite low in Nandi. So seems to me, of course, you can run this analysis later. Seems to me that Nandi has cool, low minimum temperature and high maximum temperature. So that means it has got that wide range of temperature between the minimum and the maximum, or the annual range or something like that. The range between the maximum and minimum is uh, quite high. Well, it doesn't have to be tea. You can be analyzing something else, or even you can be doing this uh, for for tea growing regions in Africa. So, for example, you might be interested in a tea growing region in Kenya. You might be interested in a tea growing region in Ethiopia. I know there is tea in Uganda. There is tea in Rwanda. There is tea in maybe Tanzania. Uh, yes, there is tea in Tanzania, not even maybe. And there is tea in Malawi. There is tea in South Africa. Yeah, South Africa. Okay, so those could be your points. We've just changed the points. Now, if you go to your map, then you need to just pick the points uh, across those. So let's say for Kenya, you go with a region in Kericho, and then for Ethiopia, you go for a region where is tea grown in Ethiopia. It should be around this region. There should be some tea somewhere here. Yeah, this is tea growing region in Ethiopia. Okay, maybe you pick one in Ethiopia. Uh, you are not done yet. You are traveling to Uganda, and then in Uganda, I'm sure there is tea to the south of this lake. That is a bit far. Where is that? Uganda. Okay, around this mountain there should be. Yeah, here are the tea fields in Uganda. Um, Pretty sure some of them, I mean, they are not only here in western part, they are even tea near Lake Victoria here for Uganda, but western region is the major tea growing region of Uganda. Then when we go to Rwanda, which is just southern part of Uganda, we can have some tea fields. I think Mata Tea Factory is basically somewhere here. Uh, this tea factory here is called Mata in Rwanda. And we pick a location maybe near that factory. Yeah, somebody will say the heat from the factory might affect the long-term temperature we are going to get. But I'm sure Mata Tea Factory didn't exist in 1950s. So, I mean, yeah, but. Mhm. You might think that it can affect, but yeah, it's maybe negligible. When we go to Tanzania, Tanzania spreads somewhere here. So where is tea grown in Tanzania? Maybe somewhere here. Um, there should be some tea fields. Uh, where are the tea fields in Tanzania? Somewhere here, there should be some irrigated farms. Not that. Where is the Tanzanian tea? Okay. Near somewhere here. Yeah. These are the tea fields in Tanzania. I think Ngwasi, around Ngwasi region. If I pronounce it wrongly, please. Huh? After getting your points in Tanzania, you might also be interested in the tea growing region of Malawi. So those ones are way south of uh, Lake Malawi in a region called Cholo or something like Cholo or Tiolo. Tiolo. Oh, interesting. Some nice agroforestry, some nice trees in the tea fields. I hope this is reducing the pest and insect infestation or something like that in Malawi. We can go way, way south to southern to South Africa. South Africa, where do we have tea? We should be having some tea in the eastern coast of South Africa. I think this is Lesotho, and we could be having some tea around this region. Yeah, these are tea fields in South Africa. So we pick another region in South Africa. So yeah, we have several. We have in Kenya, Ethiopia, Uganda, Rwanda, Tanzania, Malawi, and South Africa. We want to see the temperature values or how they vary here. So we have more, not just five. We can zip them together by the names of the points. We get our feature collection. We map uh, them, and we can see the map of all those points. Now they are Ethiopia, Kenya, Uganda, Rwanda, Tanzania, Malawi. And we can get, maybe we go with the maximum temperature for now. Anyway, teaming will still work. As you know, there is no big difference. Okay, then we map that, get the annual collection, and then we change this to TMMX and also this to TMMX. Okay, then we map it of our feature collection and then flatten the output. Now we have the maximum temperature for South Africa if we check the tail, and if we check the head, is it Kenya or Ethiopia? One of them, Kenya. Maximum temperatures in Kenya, and then we can visualize them. No, we need to change this to maximum temperature, and then we can see them. Well, you can see the variability or the differences in maximum temperature values across these tea growing countries, but we've just picked points. So temperature can vary throughout the country wildly. At the bottom is Tanzania. Basically, the region we selected for Tanzania is the coolest, and the warmest is Malawi near Tiolo. I think Malawi tea is sometimes grown under irrigation in some areas, so maybe that can justify that. And in between is Kenya, the largest tea producing country in Africa. So we are just around the temperature. The good temperatures for tea actually should be around below 28 maximum temperature. So we are well below that and above 12 degrees minimum for active tea shoot growth. Interesting. Doesn't have to be tea. And why is this information important in the first place? You might need it to do some analysis on pests. For example, you want to look at pest infestation in tea across countries, and you've liaised with the research institutes or organizations across these countries, starting from South Africa. You've talked with people in Ethiopia, Kenya, Rwanda, researchers from wherever, and you want to establish experiments at some locations which you pre-identified, then you might be interested in assessing pests. You might be interested in assessing some diseases affecting tea plant. You might be interested in yield over time, nutrients, how temperature could be affecting uptake of some nutrients across these locations, or even agroforestry, as we saw in Malawi. Maybe this is also the reason why they have these trees in the farm to provide some shade to the crops, because it's the one country that has the highest maximum temperature, threatening 28, even going to 29. And this is the mean. So probably we have some temperatures well above 30 in these locations, and that could lower tea production. So there could be many, many reasons why this data is important for you. And again, if you want to export it, you just take the, what data was it? Here, we just take the temp.df and we export it to CSV. Temp.df dot to CSV. And once we set it to CSV, we just provide it a name like country temperature, whatever it is, maximum temperature dot CSV. And then if you run that, it goes directly to your folder and you can download it and exploit, further report, do whatever you want with it. You are free to do that. As a thank you to the source of the data, you need to provide citation of the source of this data. So the source of the data is not Google Earth Engine. There are these groups of people who have worked tirelessly in 2018. Maybe they started this work in 2015 or whatever year. They've worked tirelessly to make this data available for you. So if you're using this data and you are publishing part of it, or all of it, then it is just a good thing to appreciate them by citing their work accordingly. Yeah, or you can even go and read this paper, the paper itself, which accompanied this work. Actually, in the paper, they said 1958 to 2015, but you can see we have data beyond that currently. So they are very busy behind the scenes, making sure that you have data you can comfortably use for your region of interest. Thank you for your attention.